Welcome everybody to today's lunchtime lecture by Karin Smit, who everybody knows very well by now, I think. This is effectively a mini Kimberlite conference. We have people from all over the world. So thanks for joining in. I mean, some of you, it's pretty late. Some of you, it's pretty early. Just a quick introduction. Karin earned her master's degree in geochemistry from UCT in 2008 and got her PhD in geology from the University of Alberta in 2013. From 2014 to 2020, she worked at the Gemology Institute of America in New York, first as a postdoctoral fellow, then as a research science. Karin has studied natural diamonds, and they're included in mantle host rocks and inclusions from deposits around the world. Her research has included studies that use mantle xenoliths and diamonds to investigate the mineralogical properties of the deep earth, the tectonic processes that affect the mantle and result in the formation, stabilization, and destruction of continents. I think today she's going to talk about diamonds from 3 specific localities in the Kaapvaal Craton, and it's a lot of new information, I suspect. So Karin, with that, take it away.
Thank you very much for the invitation, Craig, to speak. And thank you very much to everyone for joining. I know you guys are from all over, especially from Western Canada. Thanks for getting up at 4 in the morning. That's awesome. So I hope to keep you awake with great new data from the Kaapvaal. So we studied 3 different localities from the Kaapvaal. And what's great about this data set is that it's documenting over 2 billion years of Kaapvaal lithosphere modification, which was pretty awesome. And so here in the background, I just have some inclusion images. So there are some purple garnets, as well as chrome diopsides. And these are included in diamonds from Freshwood. This was a huge team effort. It's not just me. So for the Bobbejaan, collaborators are Steve Richardson, Ben Garden, John Gurney, Steve Shirey, Mark Schmitz. For the STAR data, Mark Schmitz, Steve Shirey, and for the Freshwood data, Michael Grace, Richard Stern, Ingrid Chin, and Gareth Davies, and all the institutions that were involved in this work are listed there on the right-hand side. So this is a combination of data. The Bobbejaan and STAR data are rhenium osmium ages for sulfide inclusions in diamonds, and the Freshwood data is using silicate inclusions and doing SMND analyses. And this was recently set up in Amsterdam by Gareth Davies and his team. So just to start off, I'll give just a quick introduction into cratons and the host rocks for diamonds, where diamonds form, etc. So cratons are areas of the Earth's crust that are extremely old. And so the reason that these Hadean to Archean continental crustal regions survive for so long is because they have a depleted lithospheric mantle below it. And so the lithospheric mantle is depleted in calcium, aluminium, and iron, other elements, compared to the more fertile peridotitic convecting mantle. So the lithosphere is less dense than the underlying asthenosphere, and it's also seismically fast compared to the global average. So the lithospheric mantle is pretty deep below the continental crust, so it's 150 to 200 kilometers deep. And so here you can see on this schematic, which is modified from Tappert and Tappert, you can see the thick continental crust below these cratonic regions. And this is where the majority of diamonds worldwide are forming. So the majority of diamonds are forming in the lithospheric mantle, but you also get other diamonds that form somewhat deeper in the transition zone to lower mantle. So the reason that most diamonds form here in the lithospheric mantle is because it has pressure and temperature conditions that are favorable for diamonds. So it has a cool conductive geotherm compared to the convecting mantle. And this is what makes it very conducive for diamond formation. So here is a global S-wave tomographic image showing at 150 kilometers depth slices. So this shows that the majority of the cratonic regions worldwide, you can actually see the thick lithospheric keel below it, which you can image through seismic tomography. So here in the Kaapvaal, we can see we have a pretty a thick lithospheric keel. So at 150 kilometers depths, we still have very fast S waves compared to the global average. So we can, in this way, you can image the lithospheric keel below worldwide cratons. And so this was imaging done by Andrew Schaefer and published in Graham Pearson's latest article on cratons in Nature. So what are the rocks in the cratonic lithosphere? So the majority of rocks are periddotites. So these are either lozolites or harzbergites or dunites that are made up of garnet, orthopyroxene, olivine. And if it does contain clinopyroxene, then it is a lozolite. So here you can see these bright green chrome dioxides, which make this rock a lozolite. If it didn't have any clinopyroxene, it would be a harzbergite. And if it contained majority olivine and some OPX, it would be a dunite, which is the most depleted peridotite here at the top of the triangle. Another important component in the lithospheric mantle is eclogite or pyroxenite. These have more basaltic bulk compositions, and there are two different models for their formation, one of which is that eclogites were emplaced into the lithospheric mantle through subduction of oceanic lithosphere. So components of these rocks can all be included in diamond, because diamond can grow in both eclogite and peridotite. And so they can incorporate portions of these rocks, so minerals from both eclogite and peridotite as they grow. So I've shown just a few examples of some minerals included in diamond. Here is beautiful orange eclogitic garnet. The other eclogitic mineral that's commonly included is omphacite, which is a sodium-rich clinopyroxene. There is chrome-rich diopside, and then purple pink peridotitic garnet. Sulfide, which is a very common mineral that we use to date diamonds. It's not easy to distinguish that distinguish the paragenesis only based on visual observation. And so for that, we need to do some additional analyses in order to determine paragenesis, where eclogitic sulfides, by and large, have low nickel contents, less than 12%, roughly 12%, whereas peridotitic sulfides have higher nickel contents, more than 12%.
Okay.
And so what we can do with minerals included in diamond is obtain an isochron age for the diamond. So essentially you're determining the time that these inclusions were encapsulated in the diamond and essentially became a closed system, and where they were shut off from any further isotopic equilibration with the surrounding mantle. And so if you have multiple inclusions in a single diamond, you have the opportunity to obtain an isochron age for the diamond itself. However, the majority of diamonds aren't spectacular like these ones, and they don't have multiple inclusions. Often you only have a single inclusion in a diamond that you can use. And so there you need to take single inclusions from multiple diamonds from the same place, and then you can obtain an isochron age for a suite of diamonds from that particular locality, or that particular paragenesis at that particular locality. So globally, diamond ages, as well as diamond stability, has often been linked to regional tectonic processes. So dating the time of diamond formation can lead to an improved understanding of how tectonic processes affect the lithospheric mantle. So in other words, did they make or break the cratonic lithosphere? And so diamonds are very useful trackers of these regional tectonic processes happening in the lithospheric mantle. So what are the processes that make or break the cratonic lithosphere? So the one is plume melting, where you have plume underplating that can deplete a large portion of the lithospheric mantle, and you can have, this is one of the ways which we think that, for example, the slave craton formed its thick lithospheric keel. The other way is through subduction. And so you have oceanic lithosphere subducting along a protocratonic nucleus, where you then have subduction and thickening of the lithospheric mantle. So both of these processes can actually also contribute to destruction of the cratonic lithosphere. And there's examples worldwide where you have plumes impinging on the cratonic lithosphere, contributing to its destruction. But you also have examples in Western North America and in China, where subduction actually contributed to weakening and eventual destruction of the cratonic lithosphere. And so here for this study, we wanted to see how diamond ages from the central Kaapvaal, how these are related to regional tectonic processes in order to understand how these tectonic processes affected the Kaapvaal lithospheric mantle. So here are the results up front, and then I'll just go through these from the oldest to the youngest, and we can discuss then what the ages mean in context with the regional tectonic processes. So here's a map of the Kaapvaal craton here in South Africa. So Freshwood in South Africa, in the Free State here in South Africa, Star Diamond Mine, and then on the Western Kaapvaal in the Kimberley block, we have some diamonds from Bobbejaan. So I'll just go through all of these ages, and then we can discuss what they mean. So the Bobbejaan diamonds are roughly 2.9. These are eclogitic diamonds. So just these aren't actually photos of the Bobbejaan diamonds. These are actually Freshwood diamonds. But just to illustrate that the Bobbejaan diamonds are actually eclogitic. And so also they were not silicates from Bobbejaan, they're actually sulfides. So this is a misleading slide, but the point is that they're eclogitic diamonds. So here's the age data from Bobbejaan. So as I mentioned, they're eclogitic diamonds, all containing sulfides. And so there were 9 sulfides that were analyzed and gave an isochron age of around 2.9 billion years or 2.87 billion years. And so this correlates really well with previous work that has been done in this region, showing that the Colesberg lineament is an old suture zone recording collision between the Wits and the Kimberley blocks. And so other diamond localities on the Kimberley block and also up north in Orapa also record these 2.9 ages. So Orapa, Zwaneng, and Kimberley also record 2.9 eclogitic diamond growth, which is thought to result then from continental collision and then percolation of carbon-bearing fluids and refertilization of the Kimberley block. In the crust, there is also a lot of evidence for the 2.9 GA continental collision. And so here in the Kraipan granite greenstone terrain, there are numerous 2.9 ages that have also been analyzed in this region. So certainly we see the effect in the mantle, but we also definitely see the effect of continental collision in the crust. And so here is a schematic from Schmitz from 2004. So this has been well established. And so hopefully the diamond ages from Bobbejaan, they aren't really controversial, and they really just confirm a tectonic model that has been previously established. And so here is the model where he shows that there has been subduction here below the Kimberley block, and there was arc magmatism, and where the Colesberg lineament then records the suture zone of this collision. Okay, so now moving on to the next oldest age, and these are the diamonds from Freshwood. So these are actually images from Freshwood, and they do have silicate inclusions. So these are some beautiful pink purple garnets and chrome dioxides from the prototypic suite at Freshwood. And so these are 2.74 billion year old diamonds. And so here is the isochron for these diamonds. So this age is based on 16 clinopyroxenes and 12 garnets. And combined, they give an age of around 2.74 billion years. And so this correlates really well with Ventersdorp magmatism in the Kaapvaal. And so here is a map that was once again taken or modified from Mark Schmidt's. And all of this green is the outcrops for Ventersdorp magmatism. And so it's a huge extent of magmatism that resulted from plume impingement on the central Kaapvaal. And now we can see actually that the diamonds were forming at the same time as this massive plume event. So here's a map I took from Humbert et al. 2019 that shows the 2.7 GA rift axis for the Ventersdorp. So they suggest that the rift axis was along here. And so that is very nearby to Freshwood, which is here, here in the Free State. So once again, just showing how the diamond ages correlate then with other ages that have been determined in the crust and also in the mantle. So here's data from Gumsley et al. 2020 that shows a lot of detrital zircon work that they did for the various plumes that are part of the massive Ventersdorp event. So there was repeated plume impingement on the Kaapvaal craton, and we can see that the diamond ages correlate really well here and with the Plattberg group. Once again, Mark Schmitz also did work on a few of the lower crustal xenoliths from the Free State kimberlites, so from Lace, from Freshwood, from Kaapvaal, and from Star, also showing the impact of the Ventersdorp on the lower crust. So these are zircons and monazites that he analyzed for their UPB compositions. So we can see that there is a massive impact then of the Ventersdorp on both the crust, at the lower crust, and then in the mantle where diamonds were forming. And so we do need to think a little bit about then how plume impingement impacts the lithospheric mantle in a way that you can have massive magmatism and some rifting occurring, but still have conditions that are conducive to diamond formation. So we also see that massive plume impact of the Ventersdorp had an impact on the lithospheric mantle itself, so on the peridotites. And so potentially this is a scenario similar to the slave craton where you had plume underplating causing a lot of melting and stabilization and thickening of the lithospheric mantle. And so potentially it's a similar scenario here at Ventersdorp where you had between 2.8 and 2.7, you had all this magmatism causing depletion of the peridotites in the lithospheric mantle. So here it's a compilation of osmium TRD ages obtained from peridotites, and you can see the massive impact of the Ventersdorp, which is the main age signature that you see in both the Wits block as well as the Kimberley block. So across the Colesberg lineament on the western block and the eastern block of the Kaapvaal, you see this 2.7 signature that dominates the majority of the ages from the peridotites. So moving on now to the 2.2 GA Freshwood diamonds. So these are eclogetic diamonds that contained a lot of these beautiful eclogetic to pyroxenitic garnets. So these are about 2.2 billion years old. And so there are 16 inclusions, 10 garnets and 6 chronopyroxenes that plot along this 2.2 GA isochron. So it's 2.196 plus or minus 61 million years. There are also a few samples that don't plot exactly on this isochron. And so we won't really discuss those further. But the main isochron is defined by 16 inclusions, so 10 garnets and 6 chronopyroxenes. And so this age correlates really well with Hekwood magmatism around 2.2 billion years ago. So once again, plume magmatism impacting the Kaapvaal lithospheric mantle and diamond formation happening around the same time. And so here's a map that I took from Leonard et al. 2020 and shows Hekpoort magmatism here in the Transvaal Basin. And so here's also the Ongeluk Formation, which is slightly older, around 2.4 on the Kimberley block. But here in the Eastern Block, in the Transvaal Basin, there's Hekpoort magmatism around 2.2 billion years ago. And so there's a range of ages here that I'm just giving for Hekpoort and for Ongeluk, just to show what the age constraints are. So we can see that the Hekpoort magmatism is pretty well constrained at around 2.2 billion years ago. So prior to the massive bushveld event, there was actually earlier plume magmatism here in the Transvaal Basin. Yeah, and so once again, we have plume impacting the lithospheric mantle, and then diamonds forming in association with that. And so here's just a slide to show that if you take the initial isotopic ratios from the isochrons, if you take the initial neodymium isotopic ratios from the isochrons, we can actually show that diamond formation occurred through reworking of older mantle lithologies. So we had incorporation likely of older minerals from older lithologies in the mantle that were then incorporated into the diamonds during diamond growth. So for the eclogitic isochron, so eclogitic diamonds formed around 2.2. If we take that initial isochron and extend that back to Chur and to DM, so depleted mantle and the chondritic mantle, if we extend that back, we see that the diamonds formed in host rocks that were at least 2.7 to 2.5 billion years old. So we simply just extend that back. We can calculate a model age for that, and we get an age between 2.7 and 2.5. And so this is kind of cool because it shows that the eclogitic diamonds at 2.2 likely formed in eclogitic host rocks that may have been the mafic underplates from Ventersdorp. So you had Ventersdorp plume magmatism, and then 500 million years later, you have diamonds forming in those eclogitic host rocks. And so the reason I say that is because there are 2.7 zircon-bearing granulites at Lace, but also at Freshwood. And so this model seems to work really well. And then the prototypic diamonds, so they formed at 2.74. If we take the initial ratio for those diamonds, we extend that back to depleted mantle and to the chondritic mantle, we can get model ages around 3.2 to 3 GA. And so this is sort of then just a minimum age for the prototypic mantle in the Eastern Kaapvaal. So it just shows that the prototypic diamonds formed in older prototype host rocks from around 3.2 to 3 GA. And certainly the oldest crust in the Eastern Kaapvaal is between 3.6 and 3.2. And the oldest mantle is at least 3 GA. And this is given by a Likobong prototype that Graham Pearson analyzed in the 90s. So really showing here that diamonds are forming in older mantle lithologies and then incorporating those minerals during diamond growth. And then the isotopes can equilibrate at this time to give us a nice isochron age. So both the 2.7 and the 2.2 diamonds at Freshwood are related to magmatism and failed drifting. And so I alluded to this earlier, as we need to think about how do diamonds then survive the heat. We have this heating and melting taking place in the lithospheric mantle and up into the crust. But how do diamonds then form and survive this event? And so potentially a similar scenario is the Victor diamonds from the Superior Craton. So Sonja Olbach obtained rhenium osmium age of around 720 million years. And the suggestion there is that the diamonds formed during continental breakup. And so the diamonds could be related to smaller scale fluids or melts away from the main axis of the rift. And so here's just some schematics from Steve Foley's review in 2008 that shows plume impingement on the cratonic lithospheric mantle. And so it is not that, like a plume hits the base of the lithosphere and then just erodes it away. it has to slowly start to refertilize the mantle and potentially oxidize it as well. So it needs to introduce water and also become more oxidized. And those things then weaken the lithospheric mantle over time so that later metasomatism can then cause the lithosphere to be destroyed. And so a lot of this depends on the oxidation state of the peridotites. And so a plume impingement and melt refertilization can slowly oxidize the mantle, thereby lowering the solidus, enabling melting to happen more efficiently later on. So this isn't just a one-step process, and potentially, plumes can impinge, but diamond growth can occur here, which is off axis to the main rift. But potentially it can also occur here in regions of the lithospheric mantle that aren't necessarily impacted by this melt refertilization. And so there's a lot of intricacies to plume impingement on the lithospheric mantle, and it depends a lot also on the architecture of the lithospheric mantle and not just how hydrated or how oxidized the peridotites are. Okay, so now moving on to the last diamond suite. These are diamonds from Star, and these are images from Mark Schmidt's, just showing how he sliced the diamonds to make the plates, and then showing what the sulfides look like prior to breaking them out to do the isotopic analyses. So these diamonds are around 1 billion years old. And so here is the isochron from Mark Schmidt's. So the isochron is defined by 7 inclusions. The diamonds are, so it's 1,000 plus or minus 33 million years. And so there are 7 inclusions that then define this isochron. There are some other detail on the isochron diagram, which we won't get into. So the main data to focus on is these green data points that define the 1GA diamond isochron. What's interesting about these diamonds is that they have a very enriched initial ratio. So if you take the initial ratio from the isochron and you plot that relative to the bulk earth, we can see that these peridotitic diamonds, or these peridotitic sulfides, have a very enriched initial osmium ratio, almost very similar to the diamonds from Bourboulon, which we spoke about earlier. So I've just plotted both of the initial ratios for the eclogitic and the peridotitic diamonds on here. And we can see that they are very similar, so similarly enriched relative to the chondritic mantle. But these 1GA ages are also seen in Koffiefontein and Jagertfontein. So this is once again data from Sonja Ulbach, and then also from Graham Pearson, showing eclogitic diamond growth at both Koffiefontein and Jagertfontein at around 1 billion years ago. So how can we explain these ages? So there's 2 main tectonic events that were happening around the Kaapvaal at around 1 billion years ago. So the one is plume magmatism from the Mkhonto plume, or the Mkhonto large igneous province. And the other is the Namakwa-Natal collision along the margins of the Kaapvaal craton at this time. And so this is taken from Lou Ashwell, showing the extent of Mkhonto magmatism going down into Southern Africa, even though the plume impingement site is thought to be in Botswana. So you can see magmatism from Mkhonto coming all the way into the Free State. So potentially that could explain heating of the lithospheric mantle at this time, which could then melt the peridotitic lithosphere and then form diamonds. However, we favor the Namakwa-Natal collision simply because we need subducting lithosphere in order to explain the enriched osmium initial ratio for, I'm going to go back one. This can explain the subducting oceanic lithosphere, can explain the enriched osmium initial ratio that we see in these peridotitic diamonds. And so the Namakwa-Natal collision was subduction and collision along the margin of of Kaapvaal between 1.3 and 1 billion years ago. And so we had diamond formation at around 1 GA forming at star. And this shows that there was heating and fluid mobilization into the more central parts of the craton as well. And so this wasn't restricted only to the cratonic margins. And so how can we then explain the prototitic diamonds with an enriched or non-chondritic initial osmium? And so we propose then that the diamond growth occurred from fluids originating in the basaltic portions of the subducting oceanic lithosphere. And so oceanic lithosphere would have more enriched osmium compositions than depleted prototype. And so these fluids with the enriched osmium would then percolate into the overlying sulfide-bearing prototypes of the Kaapvaal. The carbon and osmium bearing fluids cause partial melting and diamond formation happening in the prototypes. And there was probably some mixing of the unradiogenic osmium from the ancient prototitic sulfides that are already there with the radiogenic osmium from the subducted slabs. Okay, so here's just the summary then. So we had Bourboulon diamonds forming at 2.9. These are eclogetic diamonds that formed during collision of the Kimberley and the Wits blocks to form the proto-Kaapvaal craton. Then we had diamond formation at Freshwood, which occurred at around 2.74 in the prototitic diamonds due to magmatism from the Venterstroom. At the same locality, also at Freshwood, there are 2.2 GA eclogetic diamonds that formed due to magmatism from the Hekpoort and potentially also Ongeluk. But there was between 2.4 and 2.2, there was large-scale magmatism in the Transvaal Basin, and the 2.2 diamonds likely formed in association with that. And then just slightly to the south at Star, we have 1 GA prototitic diamonds that formed likely due to collision of the macronatal terrains. And so subduction then of the oceanic lithosphere beneath the Kaapvaal craton then introduced these radiogenic osmium fluids to form the Star prototitic diamonds. And so how does this then fit in with other diamonds from the Kaapvaal or the Kalahari cratons? So here's a compilation of diamond isochron ages from the combined Kalahari craton. And so I've just split this up into the margin of the Zim craton in Botswana, the Kimberley block, Colesberg lineament, Wits block, and Limpopo. And so here on the Wits block, they are, you can see there's more Proterozoic prototitic diamonds forming than in the Kimberley blocks, and certainly the very well-studied Orapa and Letlhakane terrains. And so the Freshwood diamonds here are 2.7. Venetia is the oldest diamonds in the eastern Kaapvaal, so Limpopo, Wits blocks. These Cullinan diamonds, the 3 GA age is actually a model age, so that likely shows the age of the lithosphere rather than the diamonds. But we can see that a lot of diamond formation we can correlate with tectonic events happening in the lithospheric keel. And so I've just mapped out the tectonic events happening here in this region and showing how well they then correlate to the diamonds. And so certainly there's a lot been happening in the Kaapvaal craton since the Archean. A lot of reworking, a lot of diamond formation. And so the diamond ages show that the Kaapvaal has experienced repeated episodes of reworking all through the Proterozoic. And this fits really well with Graham Pearson's proposal of a new definition for what a craton is, where they propose that cratons are stable for at least 1 billion years due to the protection of the lithospheric keels. But sort of the older definition was that cratons are stable since the Archean, so since 2.5. But we see that that old definition doesn't work now that we have more data and newer ideas we can see that globally, actually, the thickest lithosphere is not exclusive to the oldest crust. And that is what you can see in the seismic image that I showed, where you can see that there's thick crust, but that does a thick lithosphere, sorry, 150 kilometer thick lithosphere, but that is not exclusive to the oldest crust. And so really then cratons have experienced repeated episodes of reworking and plume impingement all through the Proterozoic. And so there are a lot of cratons that actually have undated diamonds. So I've just sort of made this block just showing all the red ones are cratons that have diamond ages, but all the black areas are sort of cratonic regions that have been studied, but not for their diamond ages. And so certainly we need a lot more work to date diamonds from more global localities, because diamond dating and correlation with tectonic events help us understand the processes that both form and destroy cratons and their lithospheric mantle. And so we have a lot more carbon dating to do. And so I'll leave it there, and hopefully you can have some discussion, and I look forward to your questions. Thank you.
Thank you, Karin. That was quite a good talk with quite a lot of data.
Yeah.
And I'm pleased to see there's a lot more data coming out. I'm sure there's going to be questions and discussions, and I'll open the floor to that now. Just either raise your hand or unmute yourself and go ahead. Do we have any questions or comment?
Or disagreements are fine too. Sonia?
Yes, of course. I'll leave the video off because also I'm having problem. I got thrown out earlier, so bandwidth here is not the best either. We've got pretty robust ages for eclogic xenolith from layers, which is basically the Freshwood cluster, right?
Yeah.
Which are 2.9 billion years. At the same time, we have pretty robust formation ages of around 2.9 billion for diamonds from Kimberley and the Beers Pool. And so I wonder whether you think that an earlier generation of diamonds might have been destroyed through the Wenderstopp event, sort of like what we had in the Superior, but we just don't have the diamond, the earlier generation diamond show that. I mean, I think it's generally good to. I think it'll be really good to contrast the correspondence between subduction diamond formation that you have in the Western Kaapvaal with what you are finding. I find that very interesting.
Yeah, I was certainly surprised by both parageneses at Freshwood, the prototitic and the eclogitic diamonds, both forming due to plume magmatism. Certainly not what I expected, but it certainly challenges our view of how diamonds form. And certainly, yeah, I'd have nothing to say that your suggestion of an earlier population of diamonds weren't destroyed. That's certainly possible because there certainly was massive heating in the lithosphere due to Wenderstopp. So there's nothing to suggest that certainly wasn't, there could have been an older generation of diamonds that were destroyed. We just don't see the evidence for that just yet, but certainly that is plausible. But as you say, just that that difference between the Eastern and the Western, where in the Western, it seems that subduction was the key to making it such a prolific diamond producer. So you had subduction from the Colesberg, but also from the Western side and the Kais-Magondi origin. And then in the Eastern block, where we had prototitic diamond formation then due to plume magmatism. But certainly we do see the collision signature, Namakwa-Natal at 1GA. So it's not there, but it is certainly a difference.
Yeah, thank you.
I see Steve-O has his hand up. Dr. Shirey, how can I help you?
Can you hear me okay?
Yes.
A little raspy in the morning here. Sorry, guys. Lovely talk, as always. Wonderful job. Sort of following on Sonia's question about the destruction of earlier diamond events and actually the effect on the seismic tomography of the Kaapvaal lithosphere. The seismically slow areas really follow the Bushveld and don't show anything similar south of the Bushveld that would indicate a huge overprinting or change in the mineralogy of the lithosphere that you could pick up, with a seismic technique. So I wonder if you have any thoughts as to how the distribution of diamond fluids might be channelized in some way that they don't really affect the seismic properties of the lithosphere. In other words, maybe they're using pre-existing distribution veins or channels that would do a good job wiping out earlier diamond generations and then keep themselves from affecting the pervasive in a wide way, affecting the mineralogy of the lithosphere.
Well, I think like we're looking at two different things, so with the seismics, you're looking at the properties of the bulk lithosphere. So what are the mineralogical properties of the prototype and eclogite that are in the lithosphere? And so it depends on whether the prototypes have experienced widespread refertilization or leusolitization, or whether they remain depleted. But then with the diamonds, we're looking at potentially smaller scale fluids. So they may not, fluid infiltration, metasomatic fluids may not have had such a pervasive effect then on refertilization of the lithosphere. So that's potentially why there could be a disconnect between the two.
Great, thank you.
No worries.
Odette, you've got your hand up.
Yeah. Hi, Karin. Thanks for the talk. Very nice and very good idea of arranging such talks and inviting us all. Thanks a lot.
All right.
I would like to know what is your view of what is the magmatic or how you translate the magmatic event into the diamond forming environment. Like you have big magmatism, and as you said, this is too much for forming diamonds. So how did you fancy any situation there? What's going on when the diamonds are formed?
I don't fancy any situation. I'm open to suggestions. Yeah, so here, I guess maybe this one, the Foley one. Yeah, so it depends on whether the diamonds form from fluids or from melts, and depends on what your definition of a fluid versus a melt is, as you guys know well. And so it also depends on the architecture of the lithosphere and how it is impacted by any melts that may traverse through the lithospheric section. And so for these diamonds, we haven't done any modeling to show whether they're fluids or melts or which one we prefer. We just know that the diamond forming medium was introduced at this time. And so, yeah, open to debate about fluids versus melts. But I mean, I suggest that in order to get away from the heating issue, maybe you're off the main axis of the rift. And so a little bit away from the plume where you had smaller scale fluids that would be responsible for diamond growth. And so certainly I think a follow-up study would be to do trace elements in these diamonds, the diamonds that were dated. So if we select some of the 2.7 diamonds and some of the 2.2 diamonds, and we do some trace elements on the diamonds themselves, we can get a better idea of whether it's melt-like or fluid-like, and really then what the impact of the plume then is on the cratonic lithosphere and what type of melts and fluids it is introducing into the lithospheric mantle. Is that sort of...
Okay, and the garnets, for example, do they show enrichment or are they metasomatic?
I'd have to get back to you on that. I have the plots, but I didn't include them in the presentation. So I can send you the rare earth plots after, and we can have a look at them and discuss what you think.
All right. Thanks.
Sue has her hand up, but it might be Lou. I'm not sure.
No, it's me this time. Thank you.
Okay.
Yeah, I'm calling in from my office. Great talk, Karin. Thank you very much. I wanted to ask that modified definition of the keel. Do you think that opens anything up for expanding where there could be diamonds and where we could get kimberlite diamonds? So yeah, I'll leave that to you.
Exactly. And so this is a question that I've posed to some of the guys from De Beers recently, trying to figure out, well, what's going on in the Namaqua Natal then? Why isn't there an economic diamond deposit in the Namaqua Natal? We certainly know there are lots of kimberlites in the Namaqua Natal, but then how does this modified definition fit in with the fact that we don't see diamond, that we don't have a diamond mine? And so in short, I don't know, but it certainly opens up the idea that we don't have to restrict our exploration only to areas that are older than 2.5, and so it's not a strict rule. And so certainly, what Clifford proposed in 1966 was just he proposed this correlation, right, between the oldest terrains and diamonds and other metallogenic components from the lithosphere. And so we see that correlation, but I don't think he meant for it to be like a strict rule of only older than 2.5. And actually, if you go back to his original paper, I think he actually says 1.5. And so I think the ideas have been sort of modified and lost in translation since Clifford's original publication. But certainly now from the seismic imaging that Graham has incorporated into his paper, it does show that you have this very thick lithospheric keel below younger crust, below crust that's 1 GA. And so certainly I think it opens up the idea that we can maybe go back and reevaluate those terrains and see if there are any economic diamonds, diamond that I don't know. Maybe.
Yeah, that's very exciting. Thanks a lot for a great talk.
Yeah, you're welcome.
I can hear Sue thinking the research funds are going to roll in. Andrew, I hope you're still online.
Yeah, he's here.
Yeah.
Are there any other questions or comments? Steve, you still have your hand up.
Oh,
Yeah, sorry, I was struggling to unmute there. I was thinking back to the question of melts versus fluids and putting a couple of ideas together here. If we go back to the old data that Jeff Harris produced early on and then followed up by Thomas, the temperatures you get from geothermal on diamond formation and lithosphere are embarrassingly close at around 1150 or something like that. And that's way above the blocking temperature for the neodymium system, which is, 800-ish or that, and way above the blocking temperature for osmium and the sulfide system. So looking at Michael and Gareth's SMND isochrons, which are beautifully equilibrated, it argues very strongly for protogenetic inclusions that have been very fully equilibrated by whatever fluid or melt is coming in a way that does a good job producing the date of diamond growth, even though those inclusions are protogenetic. I don't know if whether that argues for a melt or a fluid, but it strikes me that it might argue for a fluid because you don't see a lot of effect on, I think, on the mineralogy of the inclusions that would be related to a melt. Like if you go back to Andy Thompson's work on sublithospheric diamonds, you get intermediate inclusions that are between Morb and peridotite end members all over the place in the super deep diamond suites, but you don't seem to see that so much in the lithosphere. The eclogitic and peridotitic grains are very separated in terms of their mineralogy. So I would say that might argue for a fluid. And any thoughts on that, Karin?
Yeah, potentially. Yes, I think Dad's laughing. Once again, I think I should get these diamonds from Gareth if he's still here. I'm not sure. And if he agrees, we do some trace elements on the diamonds themselves, so that we can. I think that would be a way that we could better understand melt versus fluid. And now Dad has a comment.
well, I would just like to state that the melts are fluid. Yeah. Then, but of course, I'm understanding the the connotation here and the use of the two names is very convenient. But please remember that melts are fluid. And what we see is that most of the things that we see in diamond are not what we call like a COH-rich fluids, but rather very close to the solidus, but on the melting side of the solidus, or on the dense part of the supercritical fluids beyond the second critical endpoint.
Yeah.
So, so my worries are that, yeah, diamonds are formed around 1100, maybe 1150, maybe 1050, things like that. But the big magnetism, we talk about higher temperature. We talk about 1300, so on. And but maybe we are far from the centers. I don't know the exact geology of South Africa to tell whether, and I don't know the right pronunciation of the names, but what I call the Voorspoed, how close it is. We understood that it flows in time, but how far is it in space from the Ventersdorf magmatism?
Yeah, let me go back to that slide. I think, did I show it? I think I did. Yeah, so these guys proposed the rift axis along here, but certainly we don't know the architecture of the lithospheric mantle at depth. And so that this is what we see at the crust, but we don't know necessarily, and I should have put Freshwood on here, that would have been helpful. Yeah, so
okay,
yeah.
Here.
Yeah, like around there-ish.
Yeah, okay. Yeah.
So it's
far enough.
It's close.
Yeah.
But we don't know exactly, what the architecture of the lithospheric mantle is at depth. And so the exact sort of where the plume impacted at depth versus where it's cropping out at surface could be two different things, right? And so, yeah, I think there's a lot of unknowns that we wouldn't necessarily be able to figure out where exactly the diamonds are forming relative to where the plume was impacting. Yeah.
And one more comment, if I may, is
Sure.
that we used IR to date or to relatively date a diamond formation at Voorspoed, and we see more generations. I mean, we were interested for the paper where we wanted to look for inclusion in octahedral diamonds. We analyzed by IR a suite of diamonds that did not carry mineral inclusions, but the IR was definitely different, and we published it this year. And we distinguish 5 generations. 2 of them may fit those that we've seen here, but there are younger events of diamond formation, including octahedral diamonds. So by looking at the whole IR record, maybe we can define more events of diamond formation that are not being caught by the dating of inclusion.
I certainly agree with that. I think this is a biased sample set, right? Where it's biased towards the inclusion-bearing diamonds. And also it's biased towards large inclusions in these diamonds, the ones that we can easier measure. And so certainly I can't exclude that there weren't 10 diamond forming events at Freshwood or 20, but this is just what we can definitively date. But it doesn't mean there aren't more diamond forming events.
Yeah.
It doesn't mean there isn't also a 1 GA event, same as star. We just don't have the data for it yet, but we can't exclude that there aren't many more diamond forming events happening all through Earth's history. I mean, there could even be older diamonds, as Sonia hinted at, that could have been destroyed. So they, could have been Archean diamonds destroyed at some point, and then, but these are the only 2 well, this is a biased sample set, right? It's biased towards inclusions and biased towards large inclusions. So, I mean, there could be lots of diamond forming events in diamonds that don't have any inclusions, and we'll just, how do we date those?
Are there any more comments or queries?
I'm not sure if Steve's hand is still raised or raised again, but.
He's just taking it down.
Got that. Got it.
But, I'm really
Ingrid?
big in the scale of these events. I popped a comment in about, the analogy to synthetic diamonds, but
Yeah.
then you try and think in a Kaapvaal scale, how are these processes being driven? Because you're kind of seeing an Okondo age in peridotic diamonds up at Venetia as well. And I really appreciate Karin touching on the biased nature of our samples, because we have such a rich data set now from Freshwood, from Jwaneng, from Marapa, but the Kimberley, the other mines, which many of which are no longer working, we can't access material to go back and do these kind of pull apart studies. So we have to be very aware that we skewed by the material that we have, the methods that were available, and then just the kimberlites that happen to sample the lithosphere, and whether those are mines or not, and whether we if they are mine, there's a chance of actually getting diamonds to date. But if it's not economic, then we won't. So what's out there that we don't know? I'm just hoping that with more work and we start filling in that granularity, we'll really start to understand these processes a little bit better.
No, for sure. I agree with that. So the more diamonds we can date, the better. So I'm ready. Does anyone else have any more questions or comments?
One comment on this side, just
Hey,
on
George.
Hello.
You're still awake?
You can hear me?
Yes, I can.
I can hear you.
On geography, it's about 30 minutes drive from the south side of Ventersdorp complex to both either Lace or Freshwood.
Yeah, so I mean, geologically, that's very close.
Very close.
Yeah.
And then the other comment that I believe I can make is that there were reports in the past of diamonds at Jericho in southern Namibia,
Really?
which I think is Namakwa Natal. I don't know that geography well enough.
Oh, I'll look into that. Yeah, that's cool.
You need somebody that can dig into a De Beers archive, because as far as I know, there were diamonds recovered at Jericho.
I think Andrew's still here, so that's good.
So is Ingrid.
Yeah, we'll have to have a look.
Okay.
Frantic note taking.
Are there any more questions or comments? Maybe just one last one from me. Has anybody got any information on dating of super deep diamonds at this stage? As far as I'm aware, it hasn't been done because they don't tend to have inclusions.
Yeah, so it's a work in progress. So Galina Belanova, she had a inclusion, like I think a zircon inclusion from Juina that she dated, or that they dated, sent for dating. Evan had 2 inclusions from his Clipper diamonds that Steve Richardson then analyzed. However, there's some difficulty with that because you need to know what paragenesis your inclusion is so that you can spike effectively. And so, you add an isotopic spike, as you know, Craig. So you add an isotopic spike to your inclusions prior to analyzing them, but you need to know what the expected concentration of the element of interest is in your inclusion. So you want to try and match that. And so then if you overspike or underspike, you can introduce a lot of uncertainty into your measurement. Steve Shirey is trying to correct me here probably. So what Steve Richardson did, I think, was he made an educated guess as to what the concentration of osmium would be in these sulfides but that turned out to not be the case. And so he was able to obtain osmium isotopic compositions, but he couldn't translate that into osmium content and medium osmium isotopes. So he couldn't, yeah, Steve, just chime in. I'm probably like saying this wrong.
You want me to comment on that?
Yeah, comment away.
Yes. So Craig, so Steve and I were able to get a model age because we couldn't spike the rhenium correctly, but we were able to get a model age that was very unradiogenic. And so this particular sulfide, there were one diamond. We looked at 2 inclusions from this one diamond, and we got an Archean 2.5 billion year model age. But this is in a diamond that has the metal has iron isotopic composition that suggests it comes from altered oceanic peridotic lithosphere that's been serpentinized and formed magnetite on the ocean floor. So the interpretation that really makes the most sense geologically is that that's not really an Archean diamond that's floating around as a super deep diamond, but actually there's some ancient components in the oceanic lithospheric mantle that are inherited, which has been seen by people looking at peridotites, and all the studies in subabyssal peridotites. And this diamond has an ancient osmium component, a refractory osmium component that is from prior depletion during mantle convection. So we have an old age, but it doesn't really mean anything other than that inherited old age is inherited from the protolith and not really the age of diamond growth on that particular diamond. So
yeah, but I think just a simple way to say it is like if you only have one inclusion from one sublithospheric diamond, you're not going to necessarily get an isochron age, because for an isochron age, you need multiple inclusions, either multiple inclusions in the same diamond or multiple inclusions from the same locality. And so, I mean, sublithospheric diamond inclusions in sublithospheric diamonds are not the largest, and they are not that common. And so to get an isochron age, a time of diamond formation from a sublithospheric diamond, we would need multiple inclusions from the same place. So once again, De Beers is listening. We're ready for those analyses. If the diamonds could be.
It definitely is a work in progress.
Yes.
Are there any more comments or questions?
Wasn't there a young age? I think there was I recall a Richardson paper talking about the short time from subduction to eruption of a Juina diamond, or am I wrong?
I thought there was one from Coffee Fontaine, but it wasn't a super deep diamond.
No, it wasn't a super deep from Coffee Fontaine.
No, it was Juina that.
I think it was just, I forget the exact data in Steve Richardson's paper, but I know that the Juina from the zircon work that Galina did, and then also Steve and I have an unpublished model age of 600 million years, also from Juina, which seems to correlate with each other. And that is close in time to when subduction occurred. So
yeah.
Gareth has his hand up.
Oded,
I think it was the Bristol group actually got some very young ages from some of the super deeps from Juanina. There was some work. I think Graham did some isotope work. They weren't very well constrained, but they were clearly hundreds of millions of years rather than billions of years.
Okay, can be.
Yes, I think it like the ages that seem to be coming up for Juina is 600 million, but yeah, I think more work needs to be done on figuring that out.
So let me make a comment on Steve's data. Steve published this data on majorite with Ben Hart in a paper that they wrote in, remember the date, Karin? It's like 2012 or something like that.
Yeah, around there.
And he did neodymium and strontium isotopic compositions and got 2 determinations. These were done in 1987 at MIT. So they're back, from analytical capability of that time. But those isotopic compositions fall right on the neodymium strontium mantle array, giving you the inference that it looks like the neodymium and strontium composition of those majorites are very much like oceanic mantle, type basalts. So that would also fit with a young assessment.
Cool.
Okay, well, thank you for that. With that, I think I'll close the session. I'll stop recording, but I'll Karen, if you can stop sharing your screen, I'll leave the meeting open. We can have a bit of discussion if we want. But thank you, Karin, for your presentation. Thank you, everybody, for attending. We will get this video posted on the GSSA YouTube channel next week, probably Tuesday. And it can be revisited at will. Thank you all for attending. I'll stop recording now.
Thanks, Karin. I'm going to go now. We'll chat next week.
Yeah, we'll chat next week. I'll send you an email.
Thanks. Okay, bye.
Thank you. Thank you.